a la ciencia argentina y mi solidaridad con las científicos argentinos. Nanopores, confinement proteins. Mario worked on both ligand receptor binding and on protein translocation. Steffi and Amina worked on the protein translocation. How does confinement change ligand receptor binding equilibrium? Protein binding with nanopores and nanochannels. We model a long nanopore coated with short polymers. The polymers have terminal ligand groups. There are proteins in the solution that have receptor groups. The receptors bind to the ligands in the polymer and immobilize the proteins inside the channel. This strategy can be used, for example, to sense proteins because blocking the channel increases its electric resistance. So the resistance can inform on the concentration of protein in solution. Enzymes immobilized in nanochannels are also interesting to construct nanoreactors. The important questions that we aim to solve using molecular theory are: how is ligand receptor binding affected by nanoconfinement? Can we use the molecular theory to optimize protein binding to the nanochannels? How does the resistance of the channel change with protein immobilization? Molecular theory is a theory explicitly considers size, shape, conformation, charges, chemical state of all molecular species. Panel A shows the density of the ligands, Panel A shows the density of the proteins center of mass as a function of the distance from the surface of the ligand. There are two layers of proteins on the surface. Layering occurs because of protein-protein steric interactions and polymer flexibility. The first layer of the proteins is in contact with the surface of the channel. The second layer is more dissolved. It is broken. Look at this. Panel C shows the density of the ligands bound to polymers. Before protein binding, red line is one. The ligands show a single peak consistent with the conformation of a polymer branch. After protein binding, the line is 1, 2. Polymers rearrange and the ligand density profile matches that of the proteins in the panel. The left column map shows the fraction of volume filled by proteins versus channel radius and surface coverage of polymers. There are non-monotonic effects both of channel radius and surface coverage. There are conditions that optimize protein binding. Look at this. The center map, the column map, shows the fraction of band ligands that are bound to a protein. For small surface coverage, every ligand is bound to a protein. At high surface coverage, the fraction of band ligands decreases because of steric interaction between proteins and between proteins and ligands. The same effect was previously observed for planar surfaces. No contact. The panel on the right shows the total number of ligands that are bound to a protein. It displays the non-monotonic function of the surface coverage because the number of ligands increases with the surface coverage, but the fraction that is bound decreases. This effect causes the non-monotonic dependence of the fluid volume with surface coverage shown in panel A. Look at this. Look at this. The left column shows fraction of volume filled by proteins versus values and length of the polymers. Again, that is non-monotonic effect. Right panel shows a column map for the fraction of bond ligands. That is a polymer length that optimizes binding. The non-monotonic effect with the length of the polymer is similar to that observed with the surface coverage. This panel shows a fraction of binding versus protein concentration. The lines correspond to the ideal binding predicted by line isotope for different constants. 1, 2, 3, 4. The blue line shows the predictions on molecular theory. The molecular theory incorporates the effect of molecular interactions on binding. These effects are very important and make the ideal isotope fail to predict binding in nanochannels. The column up on the left shows the volume fraction of the four chemical proteins versus charge and radius of the protein. For a fixed charge that is a non-monotonic effect, the such a radius of the protein, the fraction of one ligands decreases with increasing protein size, steric repulsion, or charge electrostatic repulsion. So the non-monotonic effect with protein size arises because large proteins fill more space, but suffer stronger protein steric repulsion than small proteins. Right panel shows the change of ionic conductivity of the channel upon protein binding. The conductivity was estimated from the equilibrium structure of the channel using the Foreman constant Fourier approximation, which is valid for very long channels. Neutral proteins physically block the channel, so that they decrease the ionic force. This is charged proteins incorporate counterions into the channel. These counterions are mobile and increase the ionic current through the channel. So the conductance of the channel can either increase or decrease with protein binding. First conclusion. Molecular organization of the proteins inside the channel is complex. It depends on the delicate balance between electrostatics, steric repulsions, and linear receptor in nanoconfinement. The filling of the pore with proteins non-monotonically depends on polymer surface coverage and length. Channel radius and protein charge. Ideal planning isotherms do not take into account interactions and cannot predict protein binding in nanochannels. Protein binding to nanochannels changes the ionic conductance. These changes depend on steric and electrostatic factors are not trivial to predict. However, the response of the nanochannel can be controlled by engineering the charge of the polymers. Orientational pathway using protein translocation through polymer modifying nanopores. Now I will talk about our recent work where we use a realistic model for the proteins. The model describes the proteins in 3 dimensions. We describe each amino acid in the protein by a single peak with a position obtained from the protein crystallographic structure. We consider different protein positions and about 800 different protein orientations. We also consider acid-base equilibrium of polymers and all such amino acids in the protein. The goal is to study the translocation of the protein inside a nanopore decorated by negatively charged or neutral polymers. The question is how translocation is affected by protein orientation and acid-base equilibrium. We will first show results for green fluorescent protein, GFP. Molecular theory. That's it. Again, the theory explicitly considers size, shape, conformations, charges, chemical state of all molecular species. These plots show the 3G of the system versus the position of the protein. Plus, the curves correspond to the protein moving along the axis of the bond. Red curves correspond to the protein moving close to the wall. Different panels indicate different pH. The vertical lines in each symbol shows the range of free energies obtained from different rotations. Short lines indicate there is no effect on the orientation of the free. Long lines indicate a big effect. GFP has an introductory point of 6.2. The graph is negative and has a pKa of 5. For pH A, the protein and the polymer are negative, so it is invariant for translocation. For pH 5, the protein is positive and the polymer is negative, so there is attraction. GFP will be trapped in the pore. At pH 3, the protein is positive and the crush is neutral because pH is smaller than the filter. So the profile is mainly flat. Only slightly repulsive because of steric interaction. The vertical bar, a very short orientation, is not important. At pH 7, repulsions and attractions cancel, and on average, the profile is also flat. But for pH 7, orientations are important because it is a delicate balance between strong electrostatic interaction. The protein can get trapped into the pore in the orientations with the lowest strength. This means the proteins close to the wall, red curve, experience stronger electrostatic and steric interactions than those on the axis, black curve. This is because the electrostatic potential created the polymers is more negative near the wall. So energy barriers are higher. And energy walls are deeper for the proteins near the wall than for the ones near the axis. We focus now on pH 7. The left panel shows how total charge of GFP varies as a function of its position. The charge of GFP increases when it enters the negatively charged pore due to charge regulation. The negative electrostatic environment inside the pore favors the protonation of the amino acids. So basic amino acids become more positive on average, and acid ones become less negative. pH 7. This is important. The right panel shows a similar plot, but for the magnitude of the dipolar moment. The dipolar moment is also affected by charge regulation in regions where the electric field is large. This occurs mainly at the entrances because of the strong electric field and the interface between the solution and the negatively charged polymer inside the core. This is an analysis of the effect of orientation for a polymer that is. This is an analysis of the effect of the orientation for a protein that is at the pore entrance. The arrows show the polar moment of different proteins. The arrows show the orientation with the lowest triangle, and the orange arrows show the orientations with the highest triangle. When the polar moment points towards the polymers, the triangle is smaller. Panel B shows the triangle versus the component of the polar moment in axial direction. The correlation confirms the results in panels A and B, but the dispersion of the points indicates that the prediction of free energy from the polar moment is only approximate. The three-dimensional distribution of charged amino acids and degrees of dissociation are important. This is similar to the previous slide, but for a protein in the center of the body, the polar moment of the most stable orientations with the lowest trend still point to the polymers. The orientations with the highest trend, orange arrows, are aligned with the axis A, with the axis. Panel C shows the energy versus the component of the Panel C shows the energy versus the component of the polar moment in the axial direction. Panel D is the same, but for the radial direction. Again, the trends confirm results in panel A and B, but the detailed three-dimensional distribution is important, and polar moment alone cannot predict freedom. The panel shows the change in protein charge for the protein located at different positions and for different pHs. For all positions, the charge regulation T is maximum at approximately pH 7. At pH 3, the polymers are uncharged, so they cannot affect the charge of the protein. At pH 11, the protein is too far from the isolated point, so it cannot regulate charge. So charge regulation is maximum at approximately pH 7, where the polymers are negative and protein is near its isolated point. The effect is more important at port center than in other positions. Center, entrance, outside left. These are calculations for different salt concentrations. Previous results were for 0.1 mole. Here we compare with results for 0.01 mole. The first row shows the free energy, and the second row shows the variation in charge. The electrostatic interactions are stronger for salt, small salt concentration. So energy shows larger variations for 0.01 mole. pH 3 is an exception because polymer is uncharged. The variation of the charge is also larger at lower ionic state. Charge regulation is favored by lower soil concentration. This is the same as the previous slide, but for longer polymers. For pH 7, the pore-protein interaction changes from repulsive at 0.1 molar to attractive at 0.01 molar. This is because there is a delicate balance between electrostatic attractions and steric repulsion. At low solid concentration, electrostatic attractions dominate. Our results are relevant for other proteins. These plots show the trend as a function of pH and protein position for 4 different proteins. These proteins have different sizes and isoelectric bonds. At low pH, the energy is independent of the position because it is uncharged. 2, 3, 2, 3, 2, 3, 2, 3, 0. For all proteins, there is a minimum approximately pH 6. This optimal pH does not depend on the isoelectric bond of proteins, but on the polymer pK which is found. Decreasing the pH above 6 lowers too much the charge of the brush. Increasing the pH above 6 only charges the brush a little, but it decreases the charge of the brush. That is protein for attraction, even for beta-lactoglobulin, which have an isoelectric bond smaller than 6. So in the solution, it is negative at pH 6. But inside the pore, beta-lactoglobulin becomes positive because of charge regulation. Based on these results, can we define a pore that loads proteins at 1 pH and releases them at another pH? These plots show the energy versus the position of GFP. Each plot shows different pH at each half of the pore, but this is just for comparison. In the calculation, the pH is set at 4. The plots show that GFP can get trapped at pH 6. And release loading. Loading. And release at pH 3 or at pH 7. Can we trap different proteins and release them at different pHs? This plot
compares the free energy at the center of the pore versus pH for different proteins. All proteins are loaded at pH 5, 6. This is the loading pH. Loading pH. The proteins are released when the free energy is 0. For example, all proteins can be released together if the pH is smaller than 3. If the pH is increased above 6, GFP and beta-lactam will be released first. Beta-lactam, then RNAs, and then lysine. The order more or less depends on with the isolated form of these proteins. These results demonstrate that polymer modified nanopores can be designed to manipulate protein transport and release by external stimulus such as pH and ionic source. Polymeric electrostatic and steric interactions inside the pore can give rise to complex 3D landscapes, including forests, flat landscapes, and wells. One can transition between them by using an external stimulus, such as pH. Polymer modified nanopores can be designed to load proteins and release them at periodic conditions, which more or less depend on the protein isolated. The charge of the protein is affected by the presence of the polyelectrons inside the pore. It is crucial to include this charge regulation step to correctly describe the system. Further work should address the presence of multiple proteins, keeping this realistic model. Thank you very much.
Tengo una muy básica. Hay resultados experimentales de los cuales se haya probado que la tendencia con los pH de distintas proteínas coincide con... ¿No? Puedes responder en inglés.
No. Piensa por... No.
Sí.
No. Pero ARN sí, pero no proteína. Experimenta
Pero en el cual campo.
Pero nosotros predecimos algo, entonces, claro, pero esto es
Esa, ¿eh?
no, sí,
Ah,
pero
muy simple de fabricar.
sí,
Ah,
yo
claro, está en el cálculo todo es posible.
pero es muy difícil.
Es más fácil pegar el polímero a la proteína.
No. Oh, Galo. ¡Wow! Ayer. ¡Wow!
Ya lo imaginamos. Lo podemos
Sí,
imaginar.
sí. 5 PhD.
Lo puso a trabajar. Sí.
Bien, bárbaro. Es difícil porque es no, es difícil porque es hacer es por ejemplo, no bien, no chat regulation
Claro.
es key. Sí, pero por ejemplo, sí, no, es, sí, sí, ella, es, no, uy, es cierto, chat regulation, sí, es cierto. No, eso, sí. Esto es muy bueno, porque proteins es fabuloso. ¿Alguna otra pregunta?
Son documentos que ¿vieron cómo modelaron las proteínas para poner así en teoría molecular?
En la primera parte es,
Ok.
en la primera parte las proteínas tienen estructura o no. No.
Claro. Claro. Pero diga. Con volumen.
Pero en esta segunda parte sí, ya tienen estructura
Sí, sí, sí,
tridimensional,
sí.
Breve.
Sí. Núcleos son las